Okay, hi. We're gonna get started now. So, uh, who can hear me? Just raise your hands. Yeah? Great. Okay, that's a good number of people can hear. So, for those people who can hear me, do people have the VMs? Yeah? If you don't have the VM, then raise your hand and we can get the USB to you. Okay, everybody has the VM? Okay, that's good. Uh, so, if you have our USBs, then just pass it around, and when you're done with them, just pass it back maybe after the session. Okay, so for those who cannot hear us, then you're probably not listening to this as well. So if you see someone puzzled and cannot hear us, just tell them that they can watch the live stream here. Okay, so we're a little bit late because there's more people than we expected. I think more people than the conference expected as well. So we're just gonna start now. Okay, so if you have any problem starting the VM, just raise your hands and we can come around and help. Um, Otherwise, let's just get started with the presentation. The slides. Okay, so first thing, if you cannot see the icons on the desktop, just right-click and organize desktop by name, and you'll see all the folders here. Most of the examples that we will look at today, and also a lot of the examples that we don't have time to go through, they will be here. So this is the same VM that we're using for our training course that we can also do for 2 to 3 days. So today is only 2 hours. We cannot go through a lot of the things, uh, but hopefully this will give you enough stuff to get interested, and you can play around with the examples yourself. The slides are all in the slides folder here. So you can see there are 3 slide decks that we will try to go through today if we have time. Um, and this is the page that you should go to. We will paste some stuff here. There's already some links here. So if there are any links that we need to share, or any things that we need you to copy and paste, hopefully there won't be too much. They will be pasted on this page so you don't have to type them in yourselves manually. Okay, so let's get started. So in case you're in the wrong place, this is called Practical Machine Learning in InfoSec. Um, who are you? It's hard to hear you, so maybe just come talk to us later. But who are we? Um, I'm Clarence. I'm from San Francisco Bay Area, and this is what I do. My focus is machine learning in InfoSec, and this is Anto.
Okay, hi guys. I'm Anto Joseph. I'm from India. I work with Intel and I do something with IoT, machine learning, and your regular InfoSec stuff. So that's just me. Glad to be here with all of you guys. Hope you have a good time in the workshop.
Okay, so if anybody has any questions at any point in time, feel free to raise your hands. We will try to see you guys. Yeah, we have one USB coming back, so if anyone needs USBs, okay. Okay, so today's agenda, we will try to go through everything. First of all, we start with the environment, which is already done, and then we'll go through a quick crash course in machine learning. Hopefully, we won't take more than 10 minutes, and then we will look at a few practical examples on, first of all, how to build a spam classifier. Then we'll look at anomaly detection. Anomaly detection is one of the primary uses of successes in machine learning and security. Then we'll look at malware classification and look at network packet classification, and then lastly we will go into adversarial machine learning. So this training session we will try to not have any equations at all. Also, because there's not much time to talk about theory, we'll be focusing only on the practical parts of the course. Um,
So we have these cool T-shirts to give away for whoever asks the good, the best questions. So we have two of them here, right here. So pay attention, and you could get one of these. All right. So uh, in this, is this okay? Is this screen visible? in the back. Are you able to see this? Okay, all right. Okay, so scikit-learn and TensorFlow are some of the libraries that we will be using today. These are free for download. Scikit-learn is the ever popular Python library, and TensorFlow is from Google. And yeah, so first we will have some examples dealing with scikit-learn, and then we'll have some examples with TensorFlow too. And this is how we use, I mean, this is the reason why we use scikit-learn. It's very easy to get started with. If you know Python, it's the best thing ever. And it is used both for supervised, yeah. Okay, we have one USB here. So if any of you guys want a USB, please raise your hand and I'll get it to you there. Any of you guys want a USB now? Okay. Yeah. All right. Okay. So supervised. Yeah. Okay. I have a USB here. If you guys want one, just come around and pick one. Yeah. Okay. Why don't you do that?
Cool. Okay, so today we're going to focus on using scikit-learn mainly. TensorFlow, we will. TensorFlow is most commonly used for deep learning applications. So if we have time at the end of the course, we will look at that. But otherwise, it is also something that is very commonly used for machine learning, deep learning in particular. Okay, these are some of the data science libraries. We won't spend too much time talking about them. You can look them up yourselves. Um, these are things that have different use cases. So the thing about doing data science in Python is that um, every every aspect of data science, visualization, dealing with numbers, parallelization, they're all very mature and people are using them actively in production today. So it used to be the case that the toolkits in Python weren't as established or weren't as efficient as those written in native code, or something more mature used more often in scientific communities like R. But today I think things are different, so it's very convenient for us. So some things that we'll be looking at today are different kinds of classifiers that we can use in machine learning for security. So classifiers are just algorithms that help you to classify things. So for example, if you have some units of fruits, let's say, and you wanted to classify them as apples or oranges, then you can use a classifier to perform this class of classification for you. So it's just an algorithm or a program that can be used to categorize objects. And models are simply uh, the abstraction of data that the classification algorithm contains. So, for example, when you train a model, what you're doing is you're teaching the algorithm to learn some things about the objects that it's classifying, so that the model contains all the information necessary to perform the classification of A and B classes. Okay, and how we are doing evaluation of our models today will be this very common and popular technique called cross validation. Cross validation just means that we want to be able to evaluate how accurate our algorithms are after we train them, and we have a training set and a testing set. But the concept of cross validation is just that you have a validation set that is randomly selected from your training set. So each time you go through one iteration in the cross validation workflow, you're actually randomly selecting 10% or 20% or 30% of your training set to use as a validation. So in this sense, you're covering X% of your data, and you're training the model on the remaining 1 minus X%, and then you're using that to evaluate how accurate your algorithm is. Okay, so there are four different types of machine learning use cases. Um, we won't cover all of them today. We're mainly looking at regression, classification, and anomaly detection. Recommender systems are also another popular use of machine learning systems. They're very popularly seen in online e-commerce stores when you want to recommend users things to buy, or want to recommend online users other videos to watch. So this is a very successful use case of machine learning as well. Um, so what is regression? Basically, regression is you're trying to find relationship between variables. So you take in training data and then you run it through a regression learning algorithm. You end up with this model that can help you to make predictions based on the things that you have trained it on. and then in the end you have an algorithm that can help you to classify stuff and uh, basically tell you relationships between two variables. So regression is something that can be as simple as just finding relationships between two variables. In this case, we have a very simple plot of profit versus population. So imagine you're a store owner and you're trying to determine which city you want to open your next shop in. And based on plotting this graph, you can see that the existing data points you have show that there is a positive relationship between the population of the city and the profit that you get from the store in that city. So obviously it's very intuitive, and regression is something that has existed for a long time. Machine learning is nothing complicated. It's just finding relationships between variables, and then you just, in this case we're just plotting a best fit line through the data set, and you can do this by hand. And the process of training is just that you start off with an initial line, which is the model, and then you're trying to minimize the cost function, which is the error function. So in this case, the error function can be as simple as the distance between the each data point and the line. You can be it can be the mean square error or some other ways of measuring error as well. And then through a process of training, you're going through some adjustments of this model to try to minimize the cost function of the line with each data point. Yeah. So let's run a simple example here just to show you. So today we're going to be mainly focusing on uh, examples that use this tool called IPython Notebook. So if you guys open your terminal,
Is this visible in the back? Is, okay. So just start a terminal and you go into desktop uh, and there will be a folder called intro. Okay, and you type in ipython space notebook and the file that you want to open. So, so you would get an interface like this. Let me know if you have some trouble opening this. Raise your hands if you have a trouble and I'll come along.
ask them to raise their hand if they're there.
Sorry.
Raise their hand if they're there.
Yeah, okay. Are you guys here? Just raise your hands if you guys are in the same screen as this guys. Okay. How about you guys? Are you guys good? Are you guys in the same screen? Okay. Yeah, let's go. We'll try the first example, which is a simple linear regression. And this is the IPython notebook. You can run Python code line by line using IPython notebooks, and you can visualize it right here in IPython notebook. So you can press Shift Enter to run the first block of code. Shift Enter.
Yeah. So you actually run things by cell, and cells are just one or more lines of code, and each cell is independent. So when a cell is running, you'll see the star in these square brackets beside the cell, and after it's run, you'll see a number that shows up, and this number is just the count of the cells that are being run in this particular session in this Python kernel. So in this simple example, we'll just run the example. So if you can follow along, just press Shift Enter. There are various modes of operation in IPython Notebook. When the cell is highlighted in gray, you can see I'm moving between cells now. Then you are in the intercell mode. But if you want to go inside the cell, you can just press Enter, and you can see the cell changes to green highlighted. So you can then edit the lines in the cell. You want to exit back to intercell mode, just press Exit, Escape, and then you can come back here. And so let's press Shift Enter to run. What this example is the very example that we showed in the plot earlier, is the population versus profit, and we're going to show how to actually plot a diagram that can help you to visualize your data, and then do a simple linear regression on this. So doing a data.hit is just a very simple pandas function that can help you to show the first, by default, 5 lines of the data. And this just is a good way to see the format of your data. If you want to get a little bit more statistics about your data, you can do a data.describe. So this data is actually in a pandas data frame format. When you do read CSV, it actually reads it into a pandas data frame. And a data frame you can think of as a very lightweight in-memory table of your data set. And data.describe just gives you some high-level statistics about your data set. Each dimension, in this case, each dimension, we name it, we call it a dimension, but if you're from the database world, you might be more familiar with column or feature. And then it can show you the number of number of entries you have for each dimension, the mean, standard deviation, minimum, etc. So you want to plot this out, just do a data.plot. You can change the kind of plot you want and the axes. But this is what it looks like basically. So this is very basic. The cost function we have here is a mean squared error. So let's just define the cost function. I won't go into the details line by line, but you can look at it later. This is just some more manipulation. Then we want to basically try to compute the cost function here before we do any fitting. Uh, and then this is the gradient descent algorithm. Again, I won't go through line by line, but remember earlier when I mentioned that in the process of training an algorithm, what we're doing is we're basically randomly drawing a line in the data set, and then we're trying to make the model more and more accurate. We're trying to make this line be more and more accurate by computing the cost function and then moving it in a random direction, and then recomputing the cost function. And if the cost function has improved, which means the cost function is lower, then we continue moving in that direction. And there's some randomness and stochasticity in it. So this just means that we're going through a stochastic gradient descent algorithm. So if you can think of, you're trying to find the bottom of a valley, and you're doing that by randomly walking around. So it happens that you're blind and you don't know where the bottom of the valley is. So you're just walking around and you're taking small steps, and you're trying to base which direction you should go next on how much further down you have gone in your last step. So this is a good way to think about what stochastic gradient descent is. And very quickly, we won't go into a lot more of details, but performing stochastic gradient descent, which is a way of training this algorithm, which is a way of optimizing the model, gives us this, which is the line that we saw in the slides earlier. So this is a process of training, and we won't look at the rest of the example in the interest of time, but feel free to play around. There's many other examples in this intro section, and we are basically going through a lot of basic machine learning concepts that is very helpful to know about. And these are practical examples that we feel are more helpful than reading a textbook or watching online videos and classes, because you can actually see how these things work, and you can run them yourselves line by line and really understand what it's doing. So let's go back to the slides quickly. We'll be looking at a quick example on anomaly detection today. So today we'll be focusing on 3 main classes of examples for using machine learning in security. And anomaly detection is a very common case of using machine learning in security, because let's say you have a WAF, or you're monitoring server metrics, for example. What machine learning can be very useful for is to help you to not have to manually tune thresholds. So, for example, if you are trying to find a number of the number of queries that a user makes to a particular database, and you set it to be maybe the average 2 times the average number of queries that a user makes to a database. And this obviously can change over time as you have more and more users, as your user requirements change. So anomaly detection is something that's very useful and can be used to help you automatically tune and adapt to changing thresholds in your environment. So this is a simple plot of CPU utilization over time. So this is a single dimension time series plot, and you can see it's very obvious to a human that at the very end of the graph on the very right side there's an anomaly, and this anomaly can be due to various number of reasons, but a very simple method to find this would be just to define a a threshold. So let's say you set the threshold to be here, since you have never observed the CPU to go below 0.5% over the last 5 days. But what if it actually goes somewhere to 0.6%, which still looks anomalous because of the shape. You can tell that the pattern is weird, but you still want to be able to detect this. So let's try to use machine learning to try to see if we can find this anomaly. So go to this path in your VM, desktop intro, and go to 02 anomaly detection, the IPython notebook, and we're ready. Let's go there. So what we have here is just a simple example for how to do anomaly detection using machine learning. Let's run through this example. We'll quickly go through the first part without explaining much. Um, but what this is just a data set that shows you some anomalies. So you can see very clearly that in this graph that we plotted out, there are a few points that are clearly anomalous to a human, and we want to be able to find this with various methods using machine learning. So the method that we're using here is called the Gaussian estimate, and what this is, we're basically using a known distribution, a known data distribution, and then we're fitting this distribution to the data using an elliptic envelope fitting, and then we're trying to see if this fit to the distribution can help us to find if any points lie outside our expected values. Yeah, and so you see here, after using the elliptical fitting above, the anomalous points that this algorithm thinks are anomalous are labeled in red. Yeah. So again, we're not going through the code in detail here because of time, but then you should look through each line, and it should be pretty clear what this algorithm is doing. There, you can see that there are some points that maybe a human might label as anomalous, but this algorithm is not. For example, this blue point over here, it looks pretty. It looks like an outlier, but this algorithm is not treating it as anomalous. And we will look at some other ways that this can be found. So if you close this and go back to desktop, there is this folder called anomaly.
I'm sorry.
Hi, can you hear me better? Okay, thanks. So on desktop, go to this folder called anomaly. Again, we're in desktop/anomaly, and then do IPython notebook here. So in this folder, you can see that there are two. Let's just we'll just be looking at the anomaly detection example, the IPython notebook. This is a pretty long notebook. There are a few different ways that we do anomaly detection in this notebook, um, but let's just look at the very first one. So again, the first cell is just importing stuff from for Python dependencies, and what this is this data set is actually sunspots over time. Sunspots are just like solar flares that occur. It's an astronomical phenomenon, and it's very useful to be able to find anomalies in this, because whenever a sunspot occurs, then it generally means that there's some kind of meteorological event that's going to happen, and it'll be very useful to know that ahead of time. So you can see that we're doing head on the data again. We're defining a moving average. So what we're doing here is we're using moving averages to compute the standard expected output of this time series. And then if anything falls outside of this moving average, then it'll basically be an anomaly. And let's just define a few functions to plot stuff. And we can see that in this algorithm, we are having a moving average which is the green line, being fitted to the data set, which are all the black points. And every time there is a outlier, we're labeling as a star. So what is going on here is just that every few points, we are recomputing a moving average. And whenever a data point falls outside of this moving average region, then it will be considered as an unacceptable point, and it will be considered as an anomaly. Then we can very easily flag those out. There are a few other ways to look at anomaly detection. We look at elliptic envelope fitting, but a little further down, there's this thing called an isolation forest, which is quite interesting. So what this is basically a way to find if something is anomalous or not by trying to partition the data using a random forest algorithm. And it's called an isolation forest because you're basically trying to uh, isolate each single point in the data set, and then you're trying to determine if this point is anomalous or not by seeing how far down the decision tree you have to travel. The further down the decision tree you have to travel, it means that more points are clustered around it, so you have to segment them with more branches in the tree. The fewer branches in the tree you have, it means that this point is less anomalous. So again, I won't go into details because of time, but let's uh, let's go back to another example. So we're going to look at some way of spam classification. Spam classification is another popular use of machine learning. It's probably one of the earliest users of machine learning in security and fraud and abuse. Um, so has anyone done any kind of spam classification before, or any kind of classification of text before? Okay, cool, great. So this stuff probably wouldn't be too new to you, but let's just quickly go through the example.
Maybe.
So the example that we have here is meant to show the power of machine learning in achieving better results at some task that people have been trying for a long time. So spam classification is a good example because um, people have been trying to do spam classification properly for quite some time, and then suddenly when you apply machine learning to a task, we find that it can actually be solved pretty efficiently and pretty well. You can see all the cells here are already run, and actually the results are already there because it takes some time to run. So I won't be running them live here, but if you have time at home and you have about 30 minutes to spare, then feel free to run through all these examples. So what this is just basically we have a data set of spam emails and non-spam emails, which we call ham, and we're defining a way to classify them. So the very first and very simple method of classifying spam is just to use a blacklist, right? If you have a blacklist of words that commonly appear in spam emails but never seldom appear in non-spam emails like Viagra or some kind of promotion, some crazy things, right? Um, then you can very easily pick those words out and then try to calculate the probability of these emails being spam by just looking for these words. So this is not using machine learning at all. This is just a very standard and old way of looking at things. There are some things that we're using, like NLTK is a very popular toolkit for dealing with text. It's called the Natural Language Toolkit, and we're using this to convert to clean the emails, and then we're going to encode them. And basically how we're coming up with the blacklist here is we're taking the set of words that appear in all the spam emails and taking the set of words that appear in all the ham emails, and then taking the difference of this set. So all the words that don't appear in ham emails but do appear in spam emails will be the blacklist. So again, this is a very rudimentary, it's a very crude way of finding the blacklist, but it's a good estimation for showing at least what this can do. And so you can see we're building the spam words minus ham words set. And we can see that here we have a blacklist, and we're just labeling this. We're just labeling the test set. So true positive, true negatives are TP and TN, and false positives and false negatives are FP and FN. So again, our accuracy will be these two numbers divided by all the emails. So you can see that it actually doesn't do too badly. Uh, we can see that there are a lot of true positives and also a lot of true negatives, but then there's also a fairly large number of false negatives, which means that there's a lot of spam that we didn't catch. And you can think of many reasons why this would happen. Maybe a lot of the words that were used in spam emails that were not in our training set uh, were used in the test set. So we didn't get these words in the blacklist. So in the second part of the example, we will try to use machine learning and try to fix this. This is using naive Bayes, which is basically a method for looking at the probability of something belonging to a particular class given what you have seen in the past. So this is Bayes' theorem. It's a Bayesian way of looking at statistics and probability. Mm, so again, I won't go into the math behind naive Bayes, but it's one of the simplest and purest methods of machine learning. So if you're interested in it, definitely go read up on it. Naive Bayes algorithm is still one of the most popular ways to do spam classification today, and many of the most popular spam classifiers in popular email services, Yandex, Gmail, whatever, they still use naive Bayes to power a lot of their spam classification algorithms. So what we're doing here is we're doing pretty much the same thing, except we're using naive Bayes algorithm. We're using this thing called multinomial by naive Bayes, and we're using scikit-learn. So scikit-learn is just a very convenient way of using classifiers, estimators, algorithms, and we can see that we can initialize the classifier with just one line classifier equals to multinomial naive Bayes, and then what we're doing to train is just called .fit. So it's just a common API between all different kinds of classifiers. So we didn't go into the details of different kinds of classifiers today, but if you go read up, then you'll see that there's more than just a few different kinds of classifiers. There's support vector machines, there's decision trees, there's a lot of different kinds of estimators that you can use to achieve one particular task. And each these estimators just use different algorithms to learn different things about your data set. So calling .fit and then feeding in the X train and Y train just means that you're feeding in the training data set and you're feeding in the training labels. So in this case, this is supervised learning. Supervised learning just means that you are feeding in the correct labels, you're feeding in the ground truth, so the algorithms has something to learn from. There's also this other class of classification algorithms called unsupervised learning. And what this is a large number of these unsupervised learning algorithms are actually called clustering. So what you're doing is, in those cases, are basically feeding in the data set without giving it any labels. And then based on just the raw properties of the data itself, these algorithms will learn to figure out how close each data point is to each other, which will naturally form some clusters, and each cluster will then become a class of items that will be grouped together into one category. So we can call yPredict here by calling classifier.predict and then feeding in the testing data set. And this will just give us the predictions for the test set. And so there are a few convenient functions that we can use for evaluation of how well our algorithm perform. Classification report is something that's very useful because looking at accuracy alone is a lot of the time not useful. If accuracy can be very misleading because it is just a single number and you're trying to judge how well the algorithm performed with a single number, it's not very helpful if you wanted to improve how well your algorithm performed. So if you remember looking at the true positive, true negatives, false positives, and false negatives earlier, then you'll realize that looking at how the algorithm misperformed in terms of whether it categorize more things that are spam as ham or categorize more things that are ham as spam can help you to improve the algorithm a lot. So in this case, we see that using just about 10 lines of code with scikit-learn, we have increased the algorithm's accuracy all the way to 96%, which is quite close to state of the art. State of the art spam classification on this data set would be about 99%. So to get the extra few last percentage points of accuracy, we have to do a lot more work. But we won't go into that today because you can look at that yourself. But this is just a very simple example of showing how we can use a very simple algorithm called naive Bayes to achieve much better spam classification results than we did before without using machine learning.
Did we do something about overfitting and underfitting?
Uh, not,
Talk
not, Yeah.
actor of the day.
I took out those slides actually. 'Cause-
Okay. Yeah.
okay. So as I mentioned before, there's two kinds of classification algorithms: supervised and unsupervised. Uh, Supervised learning is good if you have a lot of training data that's labeled. Um, if if you have no labeled training data, then you should use unsupervised learning. If you only have a little bit of training data, then you should use something called semi-supervised learning, which is a way that, uh, which is a method for augmenting your labeled data set. So, for example, if you only have very few examples which are labeled, then you can perform clustering on them and use the very high confidence examples as your labeled training data, and then you can perform supervised learning after you have augmented your labeled data set. So here, again, we won't go through all the algorithms today, but these are some details on the algorithms that you can look through when you have time. Um, and okay, so previously we were looking at classification of only two classes. When you have classes A and B, then you can easily draw a line, just as we have shown with the linear regression earlier. And then any points that lie above the line would be belonging to class A, and any points lying below the line belong to class B. But what if you have more than just two classes? There's a few different ways that you can do it. So multi-class classification is what this is called. So let's say you have classes A, B, and C. You have three different kinds of fruits, and then you're trying to classify them. So how do you fit a model to um, to classify things into more than two categories? So the most obvious way that you can think of is one versus the rest, which just means that you have one binary classifier per class. So you have one classifier that recognizes class A versus B and C. And then you have another classifier that recognizes class B versus A and C. And obviously the last one will be C versus A and B. Um, and this is the most obvious way to do it, but it may not be great because you may not be able to capture some of the subtle differences between two different classes. So the one versus one classifier is something that is more suited to doing this. It's more computationally intensive because instead of just having n classifiers for n category, for n class classification case, you actually have n times n minus 1 divided by 2 classifications for an n class classification problem. Classifiers, I meant. So in this case, you have for every combination of pairs, you have one classifier, and then you basically combine the results of all these classifiers to get your eventual classification result. So just a visualization of what this looks like. And so now we're going through a quick visualization of decision tree learning. So this was not made by us. This is a very cool visualization that uh, was made, I think, a couple of years ago. But I think it's very useful for visualizing what decision trees are and just the process of using machine learning in classification. So can people see this properly? Is it okay?
Maybe paste that URL in the doc.
Okay, yeah. So the URL is already pasted in the doc, and it's this. So if you're interested to play around, um, just go to this document, which is on this site again, and then click on that, and you can play around with it. So this is a visual introduction to machine learning, but what it is just a visualization of how to use decision trees for classification. And this data set is not a security data set. It's something that is used to predict house prices versus other features that can describe a particular house. So let's scroll through a little bit below. But what decision trees do is you're basically drawing boundaries in your data set and you're trying to segment this data up into different sections. And eventually what you're trying to do after segmentation is to isolate single classes of data points into a single segment. So after segmenting things up, you should not you should not have any data points of multiple colors in one single segment. And you can think of this as drawing lines in a diagram like this, or you can also more intuitively think of um, drawing a tree like this. And so you can see each branch in the tree is actually a single dimension. So for example, elevation above some certain amount will go to the left, and above some certain amount will go to the right, below some certain amount will go to the left, and then in each node of this tree, um, Yeah, in each node of this tree, we will uh, branch it again based on other dimensions again. So we can see classification performing live here. This is just training, where each data point is being segmented different uh, into different parts of the tree, and then eventually each leaf of this tree will be labeled a different label. So training accuracy is 100%, but that's not the real accuracy of the algorithm. What we have to do is to check it on the test set. And you can see that the test set happens to have some wrong classifications. Wrong classifications are actually the hollow circles. And so you can see that some of these are actually wrongly classified. But it still does pretty okay. The accuracy is about 89%. But it's due to overfitting, which is an interesting phenomenon that happens when you're using machine learning in real world data sets, and your algorithm is learning too much in detail about your training data and not too much about the actual general characteristics of your data distribution. Okay, so now we'll go into another example. Do it.
Okay. So, with all that cool machine learning, let's do something with the ever existing problem of detecting excesses using machine learning. Does that sound cool? Okay, so we have this example. Can you go to that excesses folder? So go to the WAF folder. It's in your desktop, and open the reuse.py. So you can use SUBL or use sublime SUBL space reuse.py. Okay. So this is a very simple script that can be used to detect excesses. It's not very great, but it is very self-explanatory. If you see the list, which is sample data, right there on the 17th line, uh, if you can see the 17th line, we have some excesses snippets right there. So if you run this particular script, run the reuse.py. You can run it with Python space reuse.py, and it will try to predict if it is an XSS or not. So as you can see right here, they found that the first two items in the list are XSS payloads, and the rest of them are not. We'll go into detail on how the algorithm determines this, and we will find ways to bypass this too. So, what I urge you to do is edit whatever is in that list in reuse.py, put in your own XSS vectors, and see if the algorithm predicts if it is an XSS or not. So he will demonstrate one right now. So just open reuse.py, SUBL, yeah, open reuse.py, add one more item in the sample data. Yeah, yeah. Now, and run it again, save, and it says there is no XSS for hello PH days because it's not an XSS vector. How about try something which is like, which looks something like an XSS vector?
Обрезал второй этаж. Обнаружение ботнетов в корпоративных сетях путем перехватывания сетевого трафика. Татьяна Шишкова и Алексей Вишняков.
Okay, now it found that it is like an, XSS. So what I want you to try is, we are all familiar with XSS, right? So why don't you put in your own payloads and see if you can like get a false prediction, and then we will go into understand how this algorithm works. So have fun for like 5 minutes with this algorithm.
Верите Андрей
Yeah,
Яшин, Павел Земцов,
let's
Валерий
just.
Вышинский и Алексей Давидов. Станция Венера на первом этаже, там у нас будет находиться сразу несколько выступлений, озвучиваемых, юмористический Спонсором мы говорим компании «Монстр» всестороннюю поддержку мероприятия. Один из крупнейших дистрибьюторов России приглашает гостей в зону стендов
Yeah, right.
разработчика .NET, но и
Okay.
пользователей
So
мобильных приложений.
the first guy to find a bypass will get one of these T-shirts. So if you have a bypass or if you can make it predict wrong, you get a T-shirt of your choice. Yeah.
Yeah, just raise your hands if you found something that this didn't catch.
Yeah.
Should be pretty easy.
Oh yeah.
Just to-
Okay.
Приглашаем принять участие в конкурсе компании «Ростелеком». Сломай и забирай МТС крупного дома «Ростелеком». Подходите в зону противостояния конкурсному стенду и принимайте вызов. Передохнуть и насладиться чашкой кофе или свежевыжатым соком вы можете в зоне отдыха компании «Ростелеком» на первом этаже. Ждем вас!
Dear friends, try your luck in the take a break from Ross Telecom and see if you can hack Ross Telecom smart home. Come to the stand-up zone and accept the challenge. Besides, you can relax and enjoy a cup of coffee or fresh juice in the Ross Telecom lounge on the first floor. Hope to see you there.
Cool. Okay. So, as you can see, this doesn't perform very well. You kind of optimize for simplicity instead of accuracy, but there's actually a lot of stuff that you can do to detect this more accurately.
So the data set is taken from this. The data set is very small. It has like maybe 200 lines, 200, 500 lines maybe. So yeah, so it is taken from this open source GitHub project, and we should probably have a lot more data before we even try to predict what is XSS and what is not. And it should also understand the context in which it should evaluate if this JavaScript is going to execute or not. Right now, this is a very simple script. You can see how it works by just opening up the script file. This is just a test file, the reuse.py. There is another file in there. So if you can take the script.py, yeah. This is the file which generates the machine learning model, which predicts if it is an XSS or not. So you can expand this particular file to detect SQL injection and other web attacks if you have the data set for those sort of requests. So right now we just optimize this for XSS detection. If you have data sets which kind of has traffic for SQL injection or command injection, you can use those to use the same script and train it over, and this script will be able to predict if it's an attack traffic or not. So this is totally reusable, and it is very simple. It uses a logistic regression and a TF-IDF vectorizer, and
Yeah. So again, this is using TF-IDF vectorizer on n-grams with logistic regression, which probably isn't the best algorithm to use for XSS detection. But feel free to play around with it. And usually when we have time, we will get people to try using different estimators to try to improve the accuracy of the classification. But we'll just leave that to you at home. Okay, so now we'll go into, before going to the malware and packet classification examples, we want to go into another deck of slides, which we think will be more interesting to show about, to show you how AI can be used in security in a more general context. So these slides again are in the VM under desktop/slides, but you can also download them. The link is again here. So this slides AI and security. Okay, so the traditional use cases of machine learning and AI are pretty standard. Like when you go buy stuff online, then based on what you have seen in the past or based on your profile as a user, the website will recommend you things to buy. This is a very common use case of recommender systems, as I mentioned earlier. You can also use it for image recognition, which is a very popular use case recently. When you have self-driving cars, when you have some kind of VR or AR that can detect objects, they're actually using machine learning or more specifically deep learning to recognize objects. It can also be used for understanding language. So natural language processing, natural language understanding is a very big area in machine learning, which is popularly used today because a lot of, let's say, chatbots or online text understanding services have to automate the task of understanding what a human is actually saying and what a human is typing into a text box. And AI is a very popular and useful method of actually doing that. Sentiment analysis. So, for example, if you're looking at movie reviews or things that you want to figure out if someone is talking about something good or something bad, machine learning is actually very good at doing that as well. So, just looking at the trends of using machine learning in security, or just people interested in machine learning and security over time, over the last 5 years, it's been going up and it's been going up together. So actually, machine learning has been used in the fraud fighting space for many, many years. I think security in general tends to lag behind the fraud space by about 5 to 10 years. So if you're looking at how credit card fraud is usually found, machine learning is a very early and very successful way to actually look for things, look for different patterns that may indicate that your credit card has been compromised or your bank account is compromised. So by looking for certain patterns and then using probabilistic machine learning models to give you a probability that your account is being compromised, machine learning is very good at doing that. So using machine learning and security in industry is actually it's actually booming now. Fraud detection, there are companies like PayPal or Stripe or SwiftSigns that are doing very interesting stuff in fraud detection. Malware detection, there are so many companies that are doing malware detection today. And of course, you have this other class of companies that are doing authentication. So when you have a user and you want to be able to authenticate this user, how do you do that? The traditional means of usernames and passwords, I think, is dying over time because of how easily it is to be compromised with all the breaches and leaks. But there are some companies that are using different ways of machine learning authentication. For example, Google's reCAPTCHA is using mouse movements and keystrokes on captured from the front end, from the client side, to just authenticate you and to check if you're a bot or not. And there's also other companies, for example, if you're following RSA this year, then you know that the winner of RSA this year is a latent authentication, latent mobile authentication company that uses movements captured within your mobile device to try to figure out if the movements match your profile or not. So given, let's say, your footsteps or the way that you hold your phone or the way you type in your or on the touch screen on your smartphone, they can try to create a profile for how you do these things. And if it doesn't match your profile, then they'll ask for your password. So machine learning and security research is a pretty interesting field now, and it's a very lively area of research. There's a few interesting classes of problems that I think are more promising. So for fuzzing and symbolic execution, just finding vulnerabilities in software. There's stuff that you can do to guide fuzzing campaigns, to learn basically probability input functions, and to guide how to fuzz inputs and where in the program space to feed your input into in order to reduce the time that it takes to find a vulnerability in a program. Symbolic execution, of course. There's this project called Driller, which doesn't exactly use machine learning. It's a combination of fuzzing and symbolic and concolic execution. And what it's doing is it's using the output of AFL and it's using probabilistic methods to rank them based on how probable it is that this particular program path contains vulnerabilities. There is an interesting piece of MIT research that came out last year, actually 2 years ago, for automatically patching bugs that are found in code bases. And what they do is they're learning from open source bug patches, and basically from the AST level, the CFG level, they can find what bugs look like and then what patches are used to fix these bugs. So by looking at open source GitHub projects and looking at what patch was used to fix, let's say, a buffer overflow, they can look at another totally different pattern in the code and then figure out how to fix this bug in a similar way to the previous bug that was fixed in its training set. Also, binary analysis, machine learning is very commonly used to, to identify functions. Not commonly used, but it's a very useful way of identifying function entry points. If let's say you don't have any function, if you don't have access to the symbol table, this is also something that research has been shown to work. So why use machine learning in InfoSec? Basically, there are two classes of reasons. The first thing is that system complexity is exploding at a very fast rate. Bug classes grow much faster than traditional analytical capabilities of humans. So it usually takes an analyst maybe many hours or days of fuzzing to find a bug, and it takes an analyst many hours of understanding what a piece of code or complicated code base actually does in order to understand it well enough that you can identify bugs manually. So if you have some kind of learning algorithm that can identify certain patterns that bugs might be symptomatic of, then you can use machine learning to find such patterns. Also, when you have polymorphic adversaries, when you have polymorphic or metamorphic malware that try to hide their activities, then machine learning is also a good way of doing fuzzy matching. So if your matching is binary, which means that it's either yes or no, then it is very easy for a piece of malware to just change its signature a bit slightly, and then it can bypass your detection. But if everything is probabilistic and you're using fuzzy matching to give a probability of how likely this is to be an attack, then syntactic signature matching will fail and machine learning will succeed. So essentially, machine learning is just a glorified information compression method. So what you're doing is you're trying to compress information about an entire data set into a very small and compact model. And in this sense, it is just a method of lossy encoding. So if let's say you're learning about, you're feeding in the machine learning algorithm binaries and you're trying to teach it to recognize malware from non-malware, then you realize that identifying malware is actually something that is very hard to be compressed. This skill is very hard to be compressed because people spend years and years learning binary analysis and malware analysis, and it's something that cannot be very easily compressed into a few bits of information. But if you train using statistical models, if you train a model to learn based on the input data and labels what is malicious and what is not, then statistical models and algorithms can learn how to identify different features of this data set that can be used to then classify it automatically. So ML and security in the wild. These are some papers that I think are more interesting. I won't go into the details. This is spam detection using naive Bayes. It's one of the original papers um, for how they detected spam and priority in emails on Gmail, and also fraud detection using SVMs and random forest, malware detection using deep learning, phishing detection, and network anomaly detection. Again, you can look at these on your own and read the papers yourself. I think these are some of the more interesting papers in this space.
персоналу понятно, что у нас за ночь из-за утренние часы произошло уже немало
So why is
изменений
machine
в
learning not everywhere in InfoSec
новостях.
yet?
Учитывая вчерашний
Um,
вебинар, команда эпизодов
so
старается
first of
выделить
all,
позицию, но давайте так.
it's
Я
different
перед нами храню
from
сейчас
traditional
своего
use cases of
лидера,
machine
который
learning
подробно
because there's a very
расскажет,
high cost of
что
errors
произошло за
relatively.
последние
If you have a recommender
часы.
system, let's say you're trying to recommend an item to someone to buy online, if your machine learning algorithm makes a wrong prediction, then all you're losing is just the potential income that your e-commerce site can make from this person buying this thing. But if you make a wrong prediction for, let's say, a malware classifier, then essentially you have allowed a malware into your system, and this cost, you can imagine, will be much higher than someone not buying something on your website or not watching a particular video on your website. Again, the lack of training data is very easy to get labeled training data for images, let's say, because you can just place it online and people can very easily identify what is a cat, what is a dog, what is a ship, what is a car. But if you, let's say, wanted to get a labeled data set for malware, it's non-trivial because not everybody has the skills to label malware. If you give someone a binary and you wanted them to label this as malicious or not, then they actually have to have pretty advanced skills to be able to figure out the ground truth of this. Is this malicious or not? You have to spend a lot of time just to get one single label data point. And a lot of the time, it's very difficult to explain results of machine learning. So if your machine learning algorithm gives you a prediction that this is class A and not class B. Why is that? It's a lot of the time pretty hard to make this call and explain what the algorithm is doing, just because of the fact that this information is all distilled into a very cryptic model that is sometimes hard to interpret. So this can be troubling for in the security space, because let's say you want to make a very important decision about whether to let this user into your. Someone is raising a hand. Okay. Can people hear me? Uh, no, no sound. Hello, hello. Hi. Okay. Okay. Cool. Yeah, I think the sound is back. Sorry. Um, yeah, it's difficult to explain results. And machine learning also has some fundamental vulnerabilities, which we will spend some time to look at later. So the security of machine learning itself, can you hear me? Can you hear me? Okay. So the security of machine learning itself is something that is worth looking at. So before we put any system into use, we want to figure out how reliable the system is, and machine learning is no different. So over the course of the last few years, we have seen that because of how popular machine learning is getting and how useful it is in getting very good results in security in a very short amount of time and with a relatively low amount of work, we've seen that these machine learning systems have been put into production and used in products out there. But there's actually some fundamental vulnerabilities in using machine learning in security and just using machine learning in general, which we'll look at now. So I'm sure many people have seen this example on how image classification algorithms using deep learning can be misguided. Uh, in the top left, you see a picture of a panda, and there's actually a machine learning classifier that is trained with 99.9% testing accuracy on this very famous CIFAR10 dataset. Um, and this algorithm classifies this image as a panda with about 60% confidence. Then you just add in some noise. The thing about images is that you can add in random pixels into the image, and as long as the pixels are relatively uniform or they don't change the whole image by too much, the image will still look roughly the same to a human. But actually, learning algorithms don't look at uh, the general form of an image. They look at individual pixels and how these pixels relate to one another. So you can see that this supposedly 99.9% accuracy algorithm then wrongly classifies this panda as some other animal with a very high confidence. So you can see that machine learning algorithms, deep learning algorithms, don't learn to recognize images in the same way as humans do. So there are some other methods of tricking machine learning algorithms as well. During the training phase, if you feed the algorithm some data that is misleading, then it can also learn the wrong thing. So this misleading data is called shaft, which is the attack traffic, which is the red stuff. And what we're doing is we're trying to shift the decision boundary outwards. So you can think of this as the XSS detection algorithm, where it's taking real-time input from the user, and then it's making wrong decisions for what these labels are. And then based on these wrong decisions, it is retraining itself. It's trying to adapt to changing user input. And then because of this, it has shifted the decision boundary outwards. And using methods such as this, we can show that we can trick machine learning algorithms with up to 40% evasion success, even if we use the very robust methods that are supposed to be theoretically not susceptible to these attacks. There's some previous research that I did last couple of years. I presented at PhDs 2015. There are some people that also do similar attacks on real-world examples. There are some machine learning as a service platforms. MetaMind is no longer here; is bought by Salesforce. AWS and Google Cloud platforms still maintain their machine learning as a service products. So what you can do is you upload data sets to them. They don't tell you what models they use to actually do the prediction, but let's say you upload a bunch of pictures or binaries, and what these will do is they will automatically find the way to classify these classes of data points. And then what we're doing is we try to mislead them. And you can see that most of the online services can be misclassified with adversarial learning with high 90% accuracy. So again, there's another kind of exploit of when you don't know at all what kind of model this machine learning algorithm is doing. So Gmail is a very popular email service in the US. It has a inbuilt malware classifier that's built using some kind of machine learning classification algorithms, but nobody really knows what these classification algorithms are. So last year, some of the work I did included putting in a malware bin file and then trying to misclassify the algorithm so that initially it would be detected as a virus, but then after changing the binary a little bit, I can make it not be recognized as a virus anymore, even though it still retains the malicious capabilities. This is just a simple architecture of how I trained the item. I won't go into detail again. But basically, the evasion rates were about less than 50%, which is pretty good because it means that every 10 malware samples, 4 to 5 actually get through this malware classifier algorithm and it gets through Gmail's protections. So they have since changed stuff, but yeah. Okay. So in the next half an hour or so, we'll be going through two examples of that are more practical. So we'll spend some time looking at classifying network packets, and then the next one will be classifying malware. So let's go back to the VM. We'll be looking at this path, and the dataset that we're using is a very famous dataset for running tests on intrusion detection. So what this is it's a synthetic data set that was created in the 1990s, in actually 1999. Um, it was recorded in MIT Lincoln Labs, and it was recorded in an Air Force environment, the U.S. Air Force. Basically, what this is trying to do is we're trying to come up with a classification algorithm that can classify individual network packets, individual data points, as one of four categories of attacks. It can be either denial of service, it can be unauthorized access from remote machine, remote to local, or U2R, which is user to root, or it can be some kind of probing or scanning activity. So based on some features that are already generated here for us, we want to try to classify this traffic as one of these four classes. And actually, there are five classes because these are just the attacks. There's also another class called benign, which means that this is not an attack packet. So again, the links are here in this. The links are in this Google Doc. So if you want to take a look at what we're using as a data set, feel free to look at this. But otherwise, let's go back to the VM. So, so again, go back to desktop, and then we'll go into network. So we're in home ML desktop network. And again, over here, we'll open IPython notebook. Okay, so in this example, we'll be going through how you typically look at a data set, how you explore the data set, and how you can go through the process of doing unsupervised learning, unsupervised classification, in order to find classifications like this. So we'll be looking at some very common problems that you face when when you do machine learning yourself. And if you don't follow every line that we're going through here, because we're going through it pretty fast, then feel free to come back and look at this example more in detail yourself. But the first cell, of course, we're doing just imports of dependencies. Second cell, we're just defining the data drive, and we're defining where the test and train files is. We're also defining all the header names. So this is I think there's 41 dimensions in total. These 41 dimensions are all listed here. So each of these single row is a dimension or a feature, and then you have the type of the feature. So features in this dataset can either be continuous or discrete. So what does continuous and discrete mean? Continuous just means that it's a real value number. It can be something like 1.1 or 0.7, 0.5. Discrete just means that it's a symbolic variable. It's something that belongs to one or more, not one, if it's one that is not meaningful, it can be something that belongs to two or more classes of variables. So for example, protocol type can take on the values TCP, UDP, HTTP, something like that. Not HTTP, ICMP. So in this case, we are defining the header names, so we can read in this data set, and let's just read it in. We're printing out all the attack mappings. So again, we mentioned earlier that there are four different categories of attacks: R2L, DOS, U2R, and probe. And also the fifth one is benign. So in this case, the different kinds of attacks are like guest password is a route to remote to local, nmap is a kind of probe, and then port sweep is a kind of probe. SNMP get attack is a kind of DOS. So again, this is just something that we use to manipulate our data set. And so we want to print. Again, this is there's a test set. So the first thing that you want to do when you have a multi-class classification problem is to look at the distribution of your data. And you can see that this distribution is actually pretty typical of security data sets. There's usually a lot of benign traffic, and there's very few examples for real attacks. And in particular, you'll see that obviously things like DOS will have a lot more attack traffic because by definition, DOS will have a large volume of traffic compared to attacks like user to root or root or remote to local. You can see that there's a very small volume of traffic in comparison with the other classes. And this is something that may cause a problem for us later. We do the same for the test set. So again, we split our data set into two sets. It's called the validation process, and this is the training set distribution, and this is the test set distribution. Test set distribution is a little bit better than the training set, but still you see that there's a large discrepancy between the volumes of the DOS class and the U2R class. And so we want to be able to see basically what this data set actually looks like. So let's look at the describe function. In this case, the describe function is a little bit more complicated than we saw earlier because there are so many dimensions. So there are 40 something columns in this case, 40 something features. They're not all shown here. So some of these are very obviously discrete features, like the duration or source bytes, desc bytes. These are all real value numbers with a meaningful mean and standard deviation. But some things like the flag, which is an artifact of the dataset, actually take on dummy variables. What dummy variables means is just that if you have a categorical variable that can take on one of several values, then each of these values will correspond to a single dimension. So let's say you have different protocol types, TCP and UDP. Basically what you're doing is you just split this up into multiple columns. Basically you have one column called is TCP, the other column called is UDP, and this is called one-hot encoding. So you can only have one of those be true for every single symbolic feature. And so this is a typical way of doing things, dealing with symbolic variables. So something interesting that you see is that there are very different values, very different ranges of values for different features. For example, in duration and source bytes, see that the mean here is 287, whereas the mean here is 4.5 to the power of times 10 to the power of 4. And also wrong fragment is 0.02. So different features having different means and different distributions can actually be a problem, because let's say you feed your data set into a learning algorithm which doesn't know about the different distributions for each one of these features, then it actually will skew the learning towards the features that have larger values or have more extreme distributions. So what you want to do is to actually normalize each of these features so that they all have similar means and standard deviations. So they all are normalized and standardized. There's a couple of different ways to do this. But let's look at this particular dimension called duration. And you can use the standard scalar or min-max scalar. Standard scalar just means that you're scaling it to have the mean at 0 and then the standard deviation between -1 and 1. So we can use sklearn for this as well. You can see that it scales the this particular dimension to have the mean at close to 0 and standard deviation of 1, and then the minimum value is -1 and the maximum value is 1. Yeah, so min max scalar is similar, except everything is scaled to between 0 and 1. So which one to use, it really depends on what kind of classifier or estimator you're using. Sometimes the estimators README will tell you you have to pass in standard dimensions. So this depends. So in this case, we'll use standard scaling, and then we'll transform everything into standardized form, and we'll describe everything again. So here we'll try using the decision tree algorithm to give us a classification result. In this case, we see the classification result is not great. It's about 76%. This is the error, which means that the accuracy is just 1 minus this number. So we want to see if we can do better. So remember earlier we saw that there was this big imbalance in the classes. So we want to try to see if that may be the cause of the problem. Because this problem is so popular and is so prevalent in security data sets, here we'll go through a couple of methods of actually dealing with this. So scikit-learn by itself currently does not have any methods with dealing with imbalanced data sets, but there's this very useful Python library called imblearn, IMBLEARN, which we're using here. And you can actually use a few different methods to deal with class imbalance. Class imbalance is just the phenomenon that one class has a lot more data points than the other class. So you can do two methods. Intuitively, you either use oversampling or undersampling. Oversampling just means that you're artificially creating more data points in the low volume sample class, and then you're trying to create artificially more data points that belong to that class. And undersampling just means that you're selecting a subset of samples in the large class, so that your discrepancy between the small class and the large class won't be as large. So obviously you can think of many things that are wrong with these two methods. Oversampling is a bit weird because you're creating artificial data points in this particular class. So how do you know these new data points that you're creating will not skew the actual properties of this data set? There are different ways of doing this that will minimize the effect of how this will affect your data set. SMOTE is one of the state-of-the-art ways of doing this. There's also things like random oversampler, which basically means that you're learning the distribution of this particular dimension, and then you're randomly adding points that happen to fit in this dimension. Undersampling can also come with its own set of problems, even though they usually are less severe. So undersampling is bad when each data point actually contains relationships with other data points. So when you randomly undersample, a lot of the time you can miss out on some more subtle relationship between samples. So for example, if your data points always come in ABCD, ABCDE, and you sample randomly, you may get you may not get the full and proper distribution and description of your dimension. So in this case, we're using we're just showing how to use imblearn to do undersampling and oversampling. So in this case, we choose to use a combination of undersampling and oversampling, where first undersampling the large class and then oversampling the small class with SMOTE. And let's see if we can get better results. So a way that you can actually test which algorithm to use, because a question that I get a lot of the time is, how do we know which algorithm to use when you're just starting out and you're not sure which algorithm will perform better? So because it is so easy to just swap out algorithms with a common API in scikit-learn, a lot of the time it's just a good practice to try it out on many different classes of algorithms. You don't have to try every single iteration or every single variation of one single class of algorithms. Like, you don't have to try decision tree and random forest and all different kinds of isolation trees. But You can try, for example, one decision tree, one k nearest neighbors, one SVM, one logistic regression, for example, and then just try to see which one gives you the best result. And always try to figure out why that gives you a better result, whether it's an artifact of the nature of your data, whether it's some kind of property that doesn't fully reflect the true nature of your data set, or whether it's something that actually inherently can give you a better result and represent your data set's properties better.
Cycle learn image that you have with all the algorithms and how to choose the.
Yeah, yeah.
Yeah.
There is a in the slides there's a diagram for how to choose algorithms here. This can come with its own good and bad points, but there are a few of these flowcharts around. Microsoft has one, um, and this scikit-learn has one. But just take this with a pinch of salt because it's not always accurate, but it's a good way to start and to think about how to use algorithms. So again, this is our network classification example. We see that actually the state of the art performance using this data set for machine learning classification actually is about 70%. Um, no, it's about 80%. So we're performing at still the same, about 76%. So it's not the way that we're doing machine learning. That the reason that we're getting bad results is not because of class imbalance, but it's because of some other thing. We go through more examples and show that actually there's some other reasons that are causing the bad classification results. You can see that the classes are actually distributed in a pretty weird manner. So maybe these features aren't as descriptive as you hope they would be. So a lot of the time, getting bad results doesn't mean that just changing the classifier or changing the type of algorithm that you use will get you better results. A lot of the time, you have to go back to the source of the data and actually collect more meaningful dimensions. Maybe collect more features, more dimensions, or execute this in a different environment that will allow you to collect more descriptive features about your data set, and that will allow you to get better results. So the raw data and the feature engineering part will often get you much better results much faster than just changing algorithms. So in this last hands-on example, we'll look at classifying malware. Um, and classifying malware is an interesting topic because uh, basically you're classifying binaries, and binaries are just a collection of bytes that are not in human readable text form, right? So any kind of binaries can be considered any collection of bytes that don't happen to be encoded in a ASCII format or UTF-8 format can be considered to be executable binaries. And there are many different kinds of ways that you can extract features from these. Again, we won't go into all the different ways, but you can think of different environments or different levels of features that you can extract from this. Whether you look at the instruction level or the byte level or the bytecode level for some particular binaries, or you look at the function level or you look at the code source code level, there are many different ways that you can extract features. But in this particular example, we'll be looking at only the static PE features. So these are examples that you can get from the static section, just looking at the metadata of the portable executable files. And we're looking at just portable executable binaries in this case. So using PE file dump, you can get a bunch of these things, and this is a very convenient way to do feature engineering because you don't actually have to execute the files. You don't have to do any deeper kind of static analysis, but it also happens to be pretty okay because some of these features can be descriptive of what malware actually looks like. What you're trying to do is to find some features that can help you to isolate certain characteristics of binaries that can hint to the algorithm whether it is malicious or not. So, for example, some things like the
The entropy of the header.
yeah, the entropy of the header can help you to identify if a packet was being used to
Yeah.
uh, to
Pack the whole binary and stuff
right
like
to
that.
pack the whole binary for obfuscation. So let's look at the example that we have here. Again, let's go into desktop.
Okay, so while while we are looking at the example, so the malware analysis is all about finding the right features of the PE file format. We are just dealing with the PE file format, which is a Windows file format for executables, and we need to have static features which are more relevant in malware samples. So we have the test data, which is like Windows binaries, right? And we hope that Windows binaries are not malicious, so we would have a better result. And we are comparing it with some malware samples that we have. So we are trying to get features that are relevant to malware samples. So that's why we decided to go with the entropy of the header, and maybe some encryption decryption routines within the PE file is not necessarily an indication that it is a malware, but then it could be considered as one. So we take in the general features that a malware would ideally exhibit, and a much more production quality version of this would be doing some dynamic analysis on it. So there is this malware analysis platform called Cuckoo Sandbox, and they have this machine learning environment, which is the Cuckoo ML, right? And what they do is they run your binary through Radar, which is something like IDA Pro. It's a disassembler and all that, and it gets the features dynamically while the program is run, so that it has much more relevant features, which will help you to determine if it's a malware or not, rather than just doing static analysis on it, because static analysis might not be the right way. And if you look at the screen right now, we have some of the features right here, but usually MD5 is considered as a feature because we can maybe figure out if there is a hash match of the file in a virus database or something. But when it comes to the machine learning world, an MD5 won't exhibit any relationship with the malware sample that you're trying to analyze. It's a hash value, right? So we should do some good amount of feature engineering right here, so that we could extract the useful features rather than just figuring out what does the PE file output that we get. So things like minor linker version, major linker version, those things doesn't make sense in a malware analysis platform, right? But then what we will do is we'll try to run the machine learning algorithm with this particular set of features, and then later what we will do is we'll optimize some of these features and we'll see that we'll get a better result by removing features that are not really relevant for the task at hand. So that's all about feature engineering, and it is not just relevant in machine learning, but it's always applicable for any sort of task in machine learning. So if you consider a feature which is not really relevant for your task, it's just giving more data to the algorithm, and the algorithm is not all unicorns and all that. So you have to give it whatever you think is the right kind of features, and that is what we will get us better results. So let's actually run the file right now.
So in this folder in slash desktop slash malware, we have included some examples of legitimate and malicious binaries. So these malicious binaries are just PE files from virus share, and legitimate binaries we don't share here because for obvious reasons. But again, we can see these are about 200k rows of features that we have pre-extracted. So feature extraction usually takes quite some time, even if this is just very simple static metadata features. But they can still take some time, and obviously we didn't include all of the data sets here because otherwise the VM will be large. But you can try this with your own versions of binaries and code, and you can figure out how to reuse this yourself. So what we're doing here is just to explore the data set, again in IPython notebook. What we have here is we want to read in this data set that we have pre-extracted features from. And then we're going to look at the feature selection process. So first of all, we want to explore certain features that we think might be useful. We're going to look at, so we have two dictionaries here: legit binaries and malicious binaries. Obviously, as the name suggests, legit binaries are benign, malicious are malicious. So we're going to see if there's any clear differences that can immediately tell us if this feature is useful or not. And a lot of the time, manually inspecting these features, if let's say you don't have a lot of features, we only have about 140 features here. So Uh, manual inspection is pretty okay, but later we'll look at some automatic ways to actually do this in a more efficient fashion. Looking at file alignment, we see that file alignment actually maybe isn't the best feature to include because the distribution of legit binaries file alignment is pretty much similar to the distribution of malicious binaries file alignment. So we want to find something that can very clearly tell us the difference and easily help us to distinguish, based on this single feature alone, how useful this feature is in telling apart the two dimensions, the two features. So looking at something like sections max entropy, we try to plot a graph to see if this actually is a useful feature. So green is legitimate, red is malicious, and we see that actually there's a pretty clear distribution difference between the green and red. The greens, most of them have about sections max entropy of about 6, whereas very clearly the malicious binaries have a very high sections max entropy, which could indicate the use of packers because when binaries use packers, then the entropy of sections will be high. So maybe this is a good feature to include, but obviously. We cannot just manually inspect all the features. Let's say you have 10,000 features, then it will actually take a long time for you to manually inspect each one of these 10,000 features. So there must be a way to do this easily. So it so happens that some classification models allow you to use this meta transformer called select from model, and what this is doing is just because some models inherently use different features to split them and classify the data set. For example, the decision tree model uses it uses different splits on different dimensions to categorize different classes of data points. So in this case, we're using the extra trees classifier and we're using the select from model meta transformer, and it can tell us that the important features that are being used are these features. So these are just maybe it doesn't make sense to a real malware analyst, but based on our data sets, this is statistically shown to be important in classifying these data points.
Yeah, if you see see the 13th and the 14th, all our genuine PE files came from Windows, and that they have a consistent subsystem, major subsystem version, and a minor linker version, and we can see that our algorithm kind of thinks that these are the right features, so which is not really the right the right decision. So you should have a diverse data set if you want your algorithm to predict the right kind of features, because the machine learning algorithm itself tries to find similarities between your various data points, but it doesn't know that your data comes from just one single point. So if you have the data set from a various from maybe various Windows versions, this wouldn't have happened in the first place, right?
Yeah.
So yeah.
Right. So the way that this happens is not all classification algorithms can allow you to use the select from model. Things like the random forest algorithms or decision trees can, because they do random segmentation on different features, and based on how pure each segmentation path is, how well this particular split on a single dimension is able to categorize the data points that flow through this particular node in the decision tree. It can tell you how good this dimension is at classifying classifying certain data points in your data set. So let's say we only keep the top few dimensions in this data set, and we use it for our classification. And let's see how well we do.
Dear friends,
So again, in this case, we are running this live, and we have 5 different algorithms that we are running. So we can see that very quickly, random forest algorithm seems to perform quite well, giving us a 99.3, 99.4% accuracy. So this is a pretty good way to test algorithms out. You just define all the algorithms here in a dictionary, and then you just loop through the dictionary, and it can tell you which one is the winning algorithm. So the winning algorithm is random forest with a 99.4% success rate. But obviously, as I mentioned earlier, accuracy isn't a good way. It can be misleading because you may think that it's 99% accurate, so you want to deploy this. But if you look at the confusion matrix, actually, then you can see that these are the false positives and false negatives. you actually get quite a lot of binaries that are misclassified, and maybe this is not a good enough algorithm that you can deploy just as is. Yep.
Okay. So this was all done with static features. So if you want to improve this algorithm, what you could do is use something like radar and script radar engine to extract dynamic features from your data set. So maybe if you don't have a large enough data sets for your genuine PE files, may extract genuine PE files from your operating system with various versions maybe, or you could get it from random programs. You can just write a bash script to get the programs and then have a genuine collection of benign PE files as well. You can get it from the malware samples and all that. So once you do that, you can script your dynamic analysis and you can extract the features. Probably it should be a good idea to use one of these existing platforms like Cuckoo Sandbox because they already have these features extraction done. So you could maybe plug it into Cuckoo Sandbox and then get a much more better feature result and feature set, and then do the same algorithms, and we would have a better result at some point. Yeah.
Yeah. So again, just want to quickly plug this. I have a book coming out in October, and I'll be spending an entire chapter on dissecting Android malware and extracting features using different methods like static analysis, dynamic analysis, debugging, instrumentation. So if you're interested to check it out, I'll leave this slide up again. You can sign up for updates here, or it's on Amazon now. So feel free to check it out if you are interested. It's not out yet, but it'll be out in October. So one entire chapter will be spent on extracting features from binaries.
Активным игрокам достанутся ценные призы от компании. За подробной информацией обращайтесь на стенд
Okay,
компании.
so the last
Вопрос для проекта работы
15 minutes or
над
last 10 minutes, we actually
на
look
поддержку
into
формы
adversarial machine
поддержки.
learning.
We remind you once again that
And
Kaspersky Cloud
actually,
invites you to
yeah,
claim your
let's not look
patent
at the slides.
competition where you can win valuable prizes. For more information, come to the company stand in the second floor foyer. And our appreciation goes to Kaspersky Loftus Board of
So,
PhD.
Clever Hands is a library that lets you create adversarial machine learning inputs. So that's what he's trying to demonstrate right now. This library is all set up in your virtual machine, so you can try it out by yourself. It takes a while to train. So I think this is pre-trained, right?
Yeah.
Yeah.
So what this is here is we're using the Clever Hands library to train a model, and then using it to generate some input that can trick a machine learning model that was previously trained to give accurate results. So this uses Keras. Keras is something like TensorFlow. So this is deep learning. It's something that we didn't have time to cover the theory of, but there's many tutorials online. So definitely check it out if you're interested in this. Keras is a high-level API for TensorFlow that allows you to very quickly implement deep learning algorithms and models without having to write too much code. So again, all of this stuff in this IPython notebook is pre-executed and pre-trained. Took me about maybe 2 hours or 3 hours to run all of this stuff. So you can see each iteration of training takes
And as you can see, we
from
have
500 to
already
2,000 seconds. So
uh,
it actually takes some time.
advanced our
So
approach
what
and
this is we're trying to
we will
show
not
that
use
uh,
those
there's
with
some methods of
workflows.
training
Workflows are strict
of strengthening your models, because even though we saw with image examples that it can be that adversarial examples can very easily be generated to trick existing classification models. There's actually other ways that you can use to strengthen these models, and this is called adversarial training. So the general concept is just that, let's say you have a classifier, and then the adversary tries to generate some images that will trick this classifier with a very high confidence. So 99% chance that the adversary can generate pictures of cars that this algorithm will then wrongly classify as a ship. But then, let's say you generate these adversarial images yourself, and then you use this to strengthen your own machine learning algorithm. You train this with the correct labels, and then you're trying to see if doing this can actually uh, help to make your algorithm less susceptible to being tricked. And so what we're seeing here is just that We are training this algorithm, and this algorithm performs with about 96% accuracy. And then we're using this method called the fast gradient sign method, which is invented by Ian Goodfellow, who is a very famous guy in deep learning. And using this, we will try to evaluate the accuracy of this model that is recognizing handwritten digits on these adversarial examples. So you can see earlier we got about a 96% accuracy, but over here we only get about 2% accuracy. So you can see that the adversarial samples really do affect the accuracy of a trained model that was previously shown to have a very high accuracy. And again, after we get these examples, we want to train the model using the combination of the original data set and these adversarial examples. And then we want to see that the evaluation actually causes the accuracy to improve from 2% to 18% in the first epoch, then 27%, then 34%, then eventually it gets to 46%. And obviously, when you train more and more, when you generate more and more adversarial examples, it will get better and better. But again, it is still a open question whether, open research question whether this can be solved conclusively. There's many other different methods that people are thinking of to solve the problem of adversarial machine learning. And there's also research papers that are published every day. I think one was published maybe today by Nicholas Papernaut. But this is something that is pretty interesting on the frontiers of research in machine learning and security.
Even adversarial generative networks have been used not just for malicious purposes. It can be used for things like removing obstructions from a picture. So these algorithms can actually generate, learn from the existing data and generate data so that you can maybe fill in data which is not really existing. So let's think about something like you are picturing you are taking a picture of a horse and you want to superimpose a zebra on it. So you could literally do that with adversarial generative networks. So it's not just an offensive approach in machine learning. It has its uses as well. Yeah.
Yeah. So, so we're coming into the last few minutes of our workshop. There are some interesting examples that we think are fun to play with. So in the deep learning slash RNN Shakespeare section, there's a demo for a deep learning algorithm actually writing Python code. So if you run this yourself, you can see that this algorithm is actually creating Python code by itself. And what it's doing is it's being trained on the TensorFlow code base, and this is TensorFlow code being trained on TensorFlow code base to write Python code. So none of these examples none of these output is hard coded into the model anywhere. What it's doing is it's learning the structure of Python code, and after some iterations of learning how Python code looks like, and actually write some stuff that maybe makes sense. But a lot of the time it doesn't compile unless you do some kind of massaging. But if we leave it here for some time, you can see that most of the brackets are actually closed properly, and you can see very clear function. You can see very clear function structures and
Even
comments.
there are comments.
Yeah, and it will a lot of the time print out the Apache 2.0 license because it exists in every Python
Yeah,
file.
this might very well be the beginning of Skynet.
So again, this is trained using code. It doesn't actually know the meaning of the code. It's just syntactic, so it's just learning the syntax of code. In this example, there's also some other pre-trained models using the Harry Potter books, using all 7 Harry Potter books. But actually, code is much easier to learn the syntax for than English language or any other language. So it doesn't perform that well on Harry Potter. It's also trained using Shakespeare. Shakespeare performs well because the syntax of Shakespeare is pretty constrained as a language.
Yeah.
So in our final example, we want to show like there's this thing called Q learning that is basically a way to teach a deep learning algorithm to learn how to play a game. So if you go to Kara Slappy Bird and just run.sh, then what we're doing here is this is an algorithm that is learning how to play Flappy Bird. So there's just one input key, which is up, and over time the algorithm decides whether to press up or not to press anything.
So it's just how you do train a dog. If it does something good, you give it a reward. If it does something bad, you don't give it anything. So after some times, the bird becomes really good that it knows what sort of button it should press. And this game only has one button, which is like the forward arrow, and it is pretty good. I am sure that if you have tried playing Flappy Bird, it's extremely difficult to pass the one or two blocks, right? And it seems like it is doing pretty good.
Yeah, so if you see the output, which is on the printouts on the command line, there's two actions, 0 or 1. One just means that you press the up button, and 0 just means you're not doing anything. So there's actually a pretty active community of people using Q learning to play games like this. This is using some form of deep learning, using a genetic evolution algorithm to keep the paths of the model that actually performs well over time, and people use this to play Super Mario with perfect accuracy and all. And you can play around with this. You can train your own games, and it's actually a pretty simple thing to do.
Maybe train it, show how it works while it trains. It does very bad when we start the training. So we'll do an example of how it trains, and it takes a lot of time to get this good. So he'll just run,
I can't train it.
okay, okay.
But yeah, there's some dependency issues which you can't actually train it in here
Run
until
dot
you.
sh hyphen train. Okay.
Okay, so that's all we have for our workshop. Again, if you have any questions about the material here, if you want to chat with us, these are our email addresses. Um, so we'll just leave them here, um, and take a
Yeah, we'll be
picture,
around.
or like we'll chat with us on Twitter or something. Uh, and also, I want to quickly plug this book again. It's coming out in October. Um, if you're interested in the material that we have today, I'll go into a lot of detail in each chapter of the book as well. An early release is coming out in a few weeks. So, yeah, check it out.
And we are also doing a training at HITB GSEC, which is in Singapore, which is coming up in 3 months. Yeah, if you are interested to learn more, sign up. It's in Singapore. So,
Okay.
all right. So that's all from us. If you have questions, we'll be around. So.